Hi, and welcome to the lab. Today, we're gonna actually just do a really quick. I wanted to do a really quick video on a circuit that, or I should say, part of a circuit that I'm doing another video for. And this is has to do with the power supply of a power supply, and more specifically, it's the power supply of a of the reference. And so of course this power supply is a mains-based power supply, so there's a transformer and a full wave rectifier, bridge rectifier, and there's an interesting quirk that I had not seen before, which is probably normal because I haven't seen a lot, but it was the fact that and in your normal standard bridge rectifier, you've got full wave rectifier, I should say. You've got the setup we sort of have right here, right, where you've got your 4 diodes in your full bridge configuration, full wave configuration. I have a load right here between the positive, negative DC. You've got your 2 AC inputs, and you have a smoothing cap, which essentially takes the output, and the output's going to be, it's going to have ripple on it, of course. And it's going to smooth it out. So, why was this particular variant of the circuit interesting? Well, it had a cap on the input side, which I had not seen before, and it was a very small cap, and that was kind of weird. And I said, "Well, I wonder why." So I thought about it a little bit more. Asked on the EEV blog IRC channel, and got the obvious reply, and I kind of went, "Oh yeah, duh, of course." So when we have a standard full wave rectifier, bridge rectifier, we have our input wave, and it's going to look something along the lines of this, right? Which, of course, your ground point here, you're going to have positive and my negative, and the wave is going to look something like this on the input. The output, of course, is going to look something like this. And of course, the smoothed output is going to look something like this. With some DC offset here and some ripple here, peak-to-peak ripple here. And what they were saying, what the schematic was saying, was essentially that, in a normal bridge rectifier, you have your standard setup here. I'm just going to rough this in really fast. And you have your negative, positive, AC, AC. And I'm not going to go into the details here, but essentially, the interesting part is, as we are going through as we go through this wave and we put that through here, at some point here, let's take this point being 0.5 volts, and with forward voltage drop of about 0.5 volts. So they're going to start turning on roughly about here, and turn off. Turn off, turn on, turn off, turn on, and turn off here. So there's going to be this spot here, and the interesting thing is, at these points, it's not instantaneous, right? I mean, you've got your diode, and you've got your PN. You got your PN junction, of course, and as you've got your current going through it, there's a depletion zone here that gets filled in, and that allows you, and that's what you need, that forward voltage, that 0.5 of voltage drop to fill this depletion zone. At which point, then your diode is conducting, your semiconductor is conducting. Well, of course, when you reverse that, this depletion zone doesn't just enlarge and disappear instantaneously. It takes a bit of time. So it's this point here where we're switching off, right? And more specifically, it's right here when we're starting to go into the negative, or the inverted voltage, where we're actually pulling electrons out of that depletion zone, where we can actually conduct in reverse. And the interesting thing that they're talking about was, and so if you take a look at this, we normally have a cap normally, well, actually, normally it's like that. Well, if I normally have a cap, and let's say it's 10 mic or something like that. And what they're saying is there's actually a cap here of about, I think it was like 10 to 100 nanofarads. And the interesting, what they were saying is that this reverse current basically is a spike. It's a spiky sort of pulse, and that pulse can induce RF feedback into your mains input, as well as forward into your actual rectified DC voltage. So it could be, it'll be sitting on the top as an AC signal on top of there. So this capacitor is here to try and sort of just cut that out a little bit, just knock the edge off of that, and try and filter that a little bit. So I thought that was really interesting. I'd never come across that before. And the supplies that that I'm doing in another set of videos for, they're designed to be fairly low noise, if possible. So of course, what I said was, well, okay, so why don't we just try and do that? Why don't we actually go ahead, mock it up on the bench, and see what we have? So we actually have that set up right here, and I'll just kind of turn it a little bit. So we have our negative DC, our positive DC here. We have our two inputs, our AC input signal feeding the AC part of the bridge. We have a smoothing cap, which I don't remember what it is. I think it's 100 mic. Yeah, 100 mic, 16 volt. And a 470 ohm load across the outputs here. That might be a bit much, but it'll be fine for our case, because what we're interested in seeing is if this guy generates any noise. So this is the setup we have. Just gonna zoom in a little bit. The signal generator just set up for 60 hertz sine wave. Oh, here, I'm gonna point with this. So sine wave, 60 hertz. Duty cycle 50%, amplitude of 5 volts, peak to peak with an offset of 0 volts. Just sort of simulating a typical mains waveform, but of course with almost no power behind it. So we'll feed that into our circuit, and on the top we have, let me just go back down here a second. We're probing the AC inputs here with our probe, and we're going to be looking at two things. First of all, we're going to be looking, let me get it a bit closer here. So I have channel 1 set up. Channel 1 set up with that is we're scoping the input of the AC input on the full wave bridge rectifier, and then I have an FFT going here. So we can see here it's basically the at-rest noise, if you will, with the circuit powered off, or not powered, I should say. And I mean, there's still stuff that's picking up. There's some, a couple of harmonics going on here. I'm not really sure what those are. I'm not entirely convinced on how good the FFT is on here, but we're set up and configured right now, because I don't think you can read that, and I can barely read that. 10 dB per vertical division and 625 kilohertz per horizontal division, and with our center on 4.37 megahertz. So let's go ahead and turn it on. I'm going to go ahead and apply power now to the circuit, and right away you can see that the noise floor jumped right there. And in fact, where we had a few little peaks, now we're getting almost a sort of a constant noise floor here. Let's power that off again. You can see the difference. You see, and just boom, our noise just drops. We have those various peaks here, which we'll just assume are background noise of the test environment. So clearly there's something that's being re-injected there. So let's go ahead, and I'm going to actually try this for the first time. I haven't actually tested this before, so what I'm going to try, I'm going to whack a 10 nanofarad cap in there on the input, and we'll see if that makes a difference. We'll be right back. Alright, here we go. And actually, the effect is much more pronounced than I thought it would be. So, again, so we have the, here, actually, I'm going to remove the capacitor. Okay, so here's the capacitor that I'm going to use. It's 10 nanofarad, which I think is the actual value that they use in the schematic that I was looking at. And I'm going to put it in right now, and you'll see actually, so the circuit's off right now, so there's no signal, whatever. So again, turn the signal on, we get that noise floor being raised, that sort of noise, wideband noise. and then we turn that off and it disappears. So I'm going to put that in right now, and again, this is in the AC path, and you can see it already has an impact. It's already lowered the noise floor considerably, so there's definitely, it's helping with the actual environmental noise as well. But now if I turn the signal on, and I'm going to do it right now, you'll notice that our noise floor stayed relatively low now. So now we're clearly filtering out that crap that's being dumped back into the AC part of the bridge rectifier by those diodes turning off. So those pulses are no longer on there. So why don't we try something now? Why don't we go ahead and we're going to change the setup a little bit. We're going to go and probe the output and see what we get. Okay, so I'm going to turn the signal off. I'm going to remove that cap again, that filtering cap. Turn the signal back on. Not that much. There's a little bit. You can see there's a little bit of extra noise. Come on, turn it off. Back on. Back off. Let me go ahead. I'm going to just go ahead and move the signal up a little bit. There we go. So again, this is off. Back on. Again, you can see these peaks again. And clearly there's there's something there, because these look like, for all the world, like harmonics of something. That doesn't make as much of a difference, I find. Anyway, maybe there's something else that's tricky going on that I'm not catching, that would be preventing that noise from being filtered back through the output. But clearly, as you can see, it makes a massive difference on the input noise. So as you can clearly see, that 10 nanofarad capacitor on the AC input is clearly filtering out that some switching noise that's occurring with those diodes that would be normally going back right through to the mains, and of course would be coupled into whatever other equipment you have plugged into the mains as well. So this is actually a fairly important piece of filtering that I never would have thought we'd need to add. And it's also fairly important for the power supply itself. If you're going to try and guarantee some sort of low ripple, low noise, high stability output, you're definitely going to need to filter that out. Otherwise, you're going to start seeing that polluting your output signal as well. So that's that. Hope you enjoyed that. If there's any, if people are really gung ho about it, I'll go ahead and build up that other circuit and probe it with a spec anon this time. And maybe we can get a better look at that noise and sort of see, characterize it a little bit better. I'm always a little bit leery of the FFTs because I'm sure they don't tell you the full story. And it might be a better idea to look at the spectrum analyzer. Anyway, mine only goes down to 10 megahertz, so I'm not entirely sure it'll be all that useful. It'd be nice to have one that goes out to 9 kilohertz, and we could sort of see. Because I think the signals going to actually be fairly low frequency, or signals will be fairly low frequency, and they won't be in the tens or hundreds of megahertz. So, we'll see. There you go. So if you like it, great, fantastic. Glad you enjoyed it. Hope you learned something. And get back out on the bench and start building stuff. Catch you later. Cheers.